All right, welcome back. Welcome back here. All right. Um, one thing we can do is we can define a new random variable based on an existing random variable. A new random variable, I'll call it g of x, which looks like function notation, and well, you'll see why in just a second. A new random variable that depends on x. I.e., g of x is equal to x squared, or g of x is equal to the natural log of x, or g of x is equal to x squared plus 1 over x minus 1. I think you get the idea. And why we are mentioning this at this juncture is because we can talk about the expectation of this new random variable. And I'll illustrate that through an example. Let's take that standard 6-sided die roll yet again, right? Let x be the outcome of a single die roll. All right. And we're going to in this case, let capital G of x equal x squared. What is the expectation of g of x? What is the expectation of g of x here, right? Well, first, let's just get a handle on what's happening with capital G of x, okay? Because g of x is a random variable. And so if we know the probability distribution of the random variable, we just apply the definition of mean or expected value to find what the expected value is, right? So let's take a look at this. Since x could be, capital X can be 1, 2, 3, 4, 5, or 6, right? Then g of x could be, well, if x is 1, then g of x is 1 squared, that's just 1. But then when it's 2, it would be 2 squared, so that's 4. 3 squared is 9, 16, 25, or 36, right? And since there's a direct one-to-one kind of correlation here, right, that g of x is equal to 1 only when x is equal to 1, right? That would not be the case if x could be negative 1, then g of x, negative 1 squared would be positive 1, right? But that's not the case here. We don't have that. This is just a one-to-one correlation. So we can quickly make a probability table for g of x, right? Probability distribution for g of x. The probability. So there's g of x. The probability then that g of x is equal to one of these values here. So g of x is equal to 1 exactly when x is equal to 1. And the probability that x is equal to 1 is 1/6, right? So maybe what I should do here, or should have, is at the start just a table of these x values. So there's 1, 2, 3 here, 4, 5, 6. All of these probabilities is a sixth. And they'd be associated with what are the g of x values. That'd be 2 squared is 4, 9, 16, 25, or 36. But I really only need these last two rows to find the expected value then of g of x, right? This would say then that the expected value of our new random variable g of x, well, it takes on the value 1 with probability 1/6. It takes on the value 4 with probability 1/6. It takes on the value 9 with probability 1/6. 16 with probability 1/6. 25 with probability 1/6. And 36 with probability 1/6. And so we add all that together, and that is 15.13 15.17 is the expected value of the square of the die rolls. The expected value of the square of the die rolls. Okay. I'll mention, just for comparison here, in case you're thinking, why did we go through all of this? If you know that the expected value of x is, where was that example? That's this problem. No. Where is that? This problem. We know the expected value of x is 3.5. Isn't the expected value of x squared just 3.5 squared? And the answer is no. This is not equal to 3.5 squared. Go ahead and check out what 3.5 squared is in your calculator. It is not 15.17. So it's not quite that simple. So we do need to go through and make this table. All right. We can formalize what we did here, which is sort of necessary, sort of not necessary, I guess you could say. Theorem 4.1. Let capital X be a random variable with probability density or probability distribution. Probability distribution. I don't want to use the word density because that implies it's continuous. So probability distribution f of x. So this is for continuous and discrete cases. All right. Then the mean of the new random variable g of x, the mean of a new random variable g of x is defined to be, and here's where that notation is kind of nice. You're looking at the expected value of g of x. In terms of the mu notation, we would prefer to put a subscript then, so we know what we're referring to. So mu of g of x in a subscript, if you will. G of x is just a random variable. So this is literally just the same definition, but the notation is going to look a little bit more fancy because it's a function. So we say g of x times f of x, sum over all values if discrete. In the continuous case, it's the same idea, but we just integrate. If continuous, okay? This definition is maybe more important for the continuous case because you're not really able to make a table of values like you are in the discrete case, where I can list out what values the random variable can take on g of x can here, and then I'm just doing 1 times a 6, 4 times a 6, 9 times a 6, right? And you just run through the same mechanical process as you would if it was just x, where x would be 1 times a 6th, 2 times a 6th, and 3 times a 6th. In the continuous case, you need to do the integration, so you still need to know what to plug in at this stage right there. And so instead of plugging in x, you're just going to plug in g of x. And in fact, let's dive into an example in the continuous sense right away. Let's say x is a random variable with PDF f of x equaling x squared over 3 minus 1 is less than x and less than 2, 0 otherwise. So good. X squared over 3 there. Okay. And let g of x then equal 4x plus 3. Let's find the expected value of g of x. Let's find the expected value of g of x. All right. Based on this definition then, or this theorem above here, we're going to integrate over all possible values, and we'll adjust our bounds in a second based on our PDF. But it's supposed to be g of x times f of x then, dx. Okay, here we go. Bounds go from minus 1 to 2 in this problem. And g of x is 4x plus 3. So g of x, substitute that whole function in there, times f of x. F of x, our PDF is x squared over 3 dx. And now, there we go. That's the setup. So if we get to that stage, that is the new part of the problem. Then we should be good to go. We have to put on our calculus hats and try to solve the integration from there. All right, excuse me, a quick sip of coffee, and let's do the calculus. What do we got here? I might factor out the 1/3 that came with this piece right there. Integrate from -1 to 2. Of course, you can do this integral any way you see fit. And then that would leave me to distribute the x squared here to those two terms. So 4x times just x squared then is 4x cubed. Then x squared times 3 would be 3x squared. Dx there. And now I can take the antiderivative. So I've got 1/3 times the antiderivative there is going to be just x to the 4th. The antiderivative of 3x squared is just x cubed. These are very nice in this case. And then our bounds, we evaluate from -1 to 2. And I'll spare us some of the arithmetic. You plug in 2, subtract when you plug in -1. Should get a nice value of 8. Should get a nice value of 8. Okay. Awesome. All right. And that's the expected value of a function of a continuous random variable, where the function in this case is 4x plus 3. All right. Awesome. Let's spice things up. Let's spice some things up. What if... What do I have for shapes here? I don't want any of those. What does this do? Ink to shape? Nah. Yeah, no. Okay, let's just make a table by hand real quick. What if... Let's take a look at something a little bit more complicated. Let's take a joint density. 0, 1, and 2 for x. 0, 1, and 2 for y. What happened here? Something like that. And let's say we got these probabilities. 3 over 28. What is this? 9 over 28 here. And 3 over 28. These numbers might sound familiar. 3/14, 3/14, 0. Oh, I'm missing. What happened? This is supposed to be 1. This is 2. Yikes. And then 1/28 and 0, 0. Okay, this table should look familiar. We've actually used this joint PDF in many of our discrete examples when we were talking about joint PDFs before. What I want to do in this example is find the expected value of g of x, y, where what's our function? This time it's a multivariate function. We're going to extrapolate our theorem where g of x, y is x times y. X times y. All right, how would we work through this? Let's use our best intuition. X times y, okay? Well, based on the theorem here, this is a discrete case, and it says we should just do the sum over all values of g of x times f of x. Well, g of x, now, in this case, we have a multivariate function, is x times y. So how can we answer this? We'd be looking at what's the expected value of x times y. Well, now we're going to want to go ahead and sum all of the x times y values over all possible cases. What I mean by that is we would do, for example, x times y times the probability that x takes on that value, right? So what can we do here? So for example, let's take the first case. When x is 0 and y is 0, and then we can multiply it by, oh, I see, I have this button selected. I don't want that button. Yes, I want that button. Okay. What do I want here? 0 times 0. There's a 3/28 probability there's a 3/28 probability that x takes on the value 0, 0, right? And in general, that would be 0, 0 times f of 0, 0. I'm just going to write it like that for a second, okay? Plus 0, x could be 0, and y can be 1 times that probability. And so f of 0, 1, that would be 3/14. That would be 3/14. Then we can do when x is 0, y is 2. That probability would be 1/28. That's times f of 0, 2. Now I'm going to cycle through when x is 1. I'm going to go over this second column here, right? I'm basically just going to go down this second column. When x is 1 and y is 0, that would be f of 1, 0. That would be 9/28 right there. And then 1 times 1 times f of 1, 1. F of 1, 1. Plus 1 times 2 times f of 1, 2. And then I can cycle through the third column when x is 2. 2 times 0 times that probability plus 2 times 1. And why am I doing 2 times 1? I'm doing the product because the function is x times y, right? If this was like x plus y, then I'd be adding those together. F of 2, 1. The last case is 2 times 2 times f of 2, 2. And I'm writing all this out in general just so we can see the pattern here. Naturally, when one's computing this, most of these are 0, right? Because this product has a 0 in it, so that's going to 0 out. That's just going to be 0. This has a 0 in it. And I don't know what I did to get that out of there. I don't want shapes. Whatever. This has a 0 in it. This has a 0 in it. What's left? 1 times 1, that does not have a 0, so I need that. 1 times 2, this is going to 0 out. There we go. So what do we have left then is actually just these last 4 probabilities. So 1 times f of 1, 1, that is 3/14. I don't know what is happening to my stuff here. I want that off. Thank you. 1, 1, 3/14. 3/14, because that comes from here. And then what do we have? F of 1, 2. What is f of 1, 2? Well, f of 1, 2 is 0. Actually, look at that. So that's actually just going to 0 out as well. So I don't need that because that is 0. What about 2, 1? F of 2, 1, that's 0 as well. So that's gone. And then 2, 2 is 0 as well. So that's gone as well. So really, all of this computation boiled down to just this. 3/14. Kind of nice. All right. I just wanted to see that general pattern. Naturally, if I'm just computing x times the expected value of x times y, I can do that a lot faster. Okay. All right. Also mentioning and working with this joint distribution here, there's something I want to mention, is this was an expected value of 2 random variables, x and y. Can I take a look at this table and talk about the expected value of something like x? Right? When dealing with a joint distribution, I'll mention that we could find the expected value of x, I guess, or the expected value of y, depending on which random variable you want to consider alone, in 2 ways. In 2 ways, right? Option 1, to compute the expected value of x, would be to first compute the marginal of x, and then just use that to find your expected value, right? G of x is the notation for the marginal distribution. And remember, how does one get the marginal distribution? In the discrete case, we can just add up these columns, right? So the 3/28, 3/14, and 1/28 adds up to a 5/14. 5/14 here. 9/28 plus 3/14, that is 15/28. And then this is just 3/28. right? So the marginal distribution in this case, there we go. So in this problem, we could get the expected value of x here. Expected value of x would be equal to 0 times 5/14 plus 1 times 15/28 plus 2 times 3/28. And that would be the expected value of x. All right. What's the second way of finding the expected value of x? The second way of finding the expected value of x is actually just to go over all of the possible values. All right. So this would be to sum over expected value of x first equal to the sum over all x values, and just use all of the probabilities that are given in your table here. Use all of these probabilities, right? So then I should have 9 things to multiply and add up. So what do I do there? I'm going to take x times each of those values. So I'm going to have to sum x times each of those values, and I need to do those for all of the y values. So in this case, it would be, for example, if y is equal to 0, x can be 0, 1, or 2, right? So I can do what here? X could be 0. So I'm going to say it's 0 times 3/28 plus 0 times 1/14 plus 0 times 1/28. And then I keep going. Plus 1 times, when x is 1, that's 9/28. Plus, when x is 1 times, now I'm at the 1, 1 case, 3/14. And so on and so forth. Okay? But now that might look a little overkill, and it is, right? Because again, think about what you're actually doing here. This right here, that is by definition the marginal distribution g of x, right? That sum is by definition the marginal distribution g of x. And look at this computation right here. I can factor out that this is weird with the 0, but I can factor out the 0. This is 0 times 3/28 plus 1/14 plus 1/28. What is adding these probabilities up? That's adding up that first column. That's going to give me the 5/14. This is 0 times 5/14, right? So these are actually equivalent things. That gives me this computation right there, okay? So I would definitely prefer to work in the first method, but just to be aware that that's sort of an alternative way of thinking about it. All right. I think we're going to leave it there. You do have comments, questions, or concerns, there's a multitude of practice problems online to work through these. So post those in the discussion thread below. I'm not doing an example of every type of problem. There's just a lot of them, and I don't want to, I'd rather you spend time working on them and maybe asking questions than there being multiple hours of video lectures for you to watch. So I'm going to leave it at that for this section here, and I look forward to seeing the discussion in the boards below.